Welcome back to the deep dive. Today we're going deep on software design and architecture, using Robert C. Martin's clean architecture. And wow, you've given me quite the stack of material. Excerpts from the foreword, the table of contents, even some pretty hefty chapters.
It looks like you're interested in the fundamentals, huh? What makes for good software architecture
Yeah,
and what doesn't? How different programming paradigms come into play and those principles for creating systems that are, built to last and adapt.
exactly. And it's not all theory either. We've got some of Martin's own war stories from Appendix A, decades of experience on actual projects.
That's where the rubber meets the road, right?
Yeah.
You can learn all the principles in a textbook, but seeing how they play out in the wild, that's where the real learning happens.
Totally. Okay, so one of the first things that jumped out at me was this quote. Software architecture doesn't look like anything. I gotta admit, that kind of threw me at first.
Oh, it's brilliant, though. We get so hung up on diagrams and visualizations, but those are just one view, often skewed by what someone chose to highlight. Like, think of a blueprint for a building. You wouldn't mistake the electrical diagram for the floor plan, would you?
Right, right. Each view tells a different part of the story. So if it's not about pretty pictures, what is software architecture then? The big idea, I mean.
Grady Booch, he nailed it. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change.
Cost of change, so it's thinking long term. How hard will it be to adapt this thing down the line when things change?
Yeah,
Because they always do.
exactly. It's that tension every architect faces. Do you prioritize making something that works perfectly right now or something easy to change later? Lean too far either way and you're in trouble.
Yeah. The book uses this example, a system that never breaks, but you can never change it. On the flip side, imagine one that's super adaptable but breaks all the time.
Yikes. And that's why maintainability is so crucial. Martin paints this vivid picture, that classic graph, where productivity just plummets over time as a code base becomes this tangled mess.
Ugh, I can feel the frustration in building just thinking about it. So how do we avoid that? What are the building blocks of good architecture?
Martin gets into all these programming paradigms, right? Structured, object-oriented, functional.
He does. It can get a bit technical, but essentially they're different approaches to handling complexity, managing change. Let's start with structured programming. It might seem basic now, but back in the day, revolutionary.
A revolution. Tell me more.
Back then, programs were this mess of go-to statements jumping all over the place. Structured programming introduced functions, loops, conditionals. Suddenly, you could actually prove your code worked, test it properly.
No more crossing your fingers and hoping for the best.
Exactly. It brought this rigor that was missing, a foundation for everything that came after. Wow, fascinating. It's like going from building with random scraps of wood to having standardized lumber blueprints. So how does object-oriented programming, OO, fit in? That's been the dominant paradigm for a while, hasn't it?
It has. And there's this myth that OO is just like data and functions mashed together into objects. Martin really pushes back on that. He says, O languages haven't brought anything new conceptually, but they make existing techniques safer, more convenient.
So not brand new ideas, but a better way to do them.
Yeah, like polymorphism. In older languages, you might have done it with complex conditional statements. O languages make it more elegant through inheritance interfaces.
All right, so it's streamlined things, but how does that connect to architecture specifically?
One big benefit is dependency inversion. Imagine building a car. Traditionally, the engine might be directly coupled to a specific transmission. But with dependency inversion, you've got this interface, a set of standards both the engine and transmission follow.
So instead of direct connection, they talk through this agreed upon standard.
Exactly. You could swap out the transmission for a different model as long as it fits that interface.
Yeah.
The engine doesn't care about the specifics anymore, just that it can send and receive the right signals.
It's like interchangeable parts. Makes your car or your software way more adaptable.
Precisely. And for architects, this is huge. It lets them create systems that are more flexible, modular.
Okay, that clicks. We've got structured. Mm-hmm. What about functional programming? That's been getting trendy lately.
It has, for good reason. One key concept is immutability, the idea that once data is created, it can't be changed.
Like a history book. Once an event's recorded, you can't go back and alter it, which, come to think of it, makes a lot of sense for software, too.
Exactly. Now, this might sound limiting, but it has huge benefits for concurrency, when you've got multiple processes happening at once.
I can see how that gets tricky. Two processes trying to change the same data. Chaos.
Yep. But if data is immutable, you eliminate that risk. No more worries about race conditions, data corruption.
So peace of mind, especially in complex systems. I like it. How does this tie back to architecture, though?
Good architects, they aim to segregate the mutable parts of a system from the immutable ones. Languages like Clojure, which are heavily influenced by functional programming, have mechanisms like atoms for managing controlled mutation.
Atoms, like the tiny building blocks of matter.
Not quite. Here, an atom is a special data structure, allows changes, but ensures they happen in a very specific, controlled way.
So you can make changes, but carefully, to keep things consistent and avoid those concurrency nightmares. Clever.
It is, and this focus on managing mutability, it's a hallmark of good architecture, regardless of which specific paradigm you're using.
Speaking of hallmarks, Martin talks about the solid principles, right? 5 principles for object-oriented design.
Yep. They're all about making code easier to maintain, extend, understand. We could do a whole deep dive on just solid, but let's focus on one that trips people up, the single responsibility principle.
Okay, hit me. What's the catch? It sounds straightforward enough. One module, one thing, right?
That's the common misunderstanding. The real focus is on a module being responsible to a single actor.
Single actor. Okay, I think I need an example for this one.
Imagine a payroll system. There's a function to calculate regular hours worked. Seems simple. But what if both the CFO, who uses it for payroll, and the COO, who uses it for scheduling, need slightly different versions of that calculation?
Ah, I see the problem. Now that one function serves 2 masters, changes for one could break things for the other. Recipe for disaster.
Exactly. So it's not just one module, one thing. It's one module, one reason to change. One actor, one need.
Wow, that's deeper than I initially thought.
Yeah.
Really understanding those stakeholders, making sure your code meets their needs without unintended consequences.
Precisely. Minimizing those ripple effects, building systems that are cohesive, well-defined. Which brings us to the next level, component principles. How do we group these modules into larger, manageable structures?
Okay, that makes sense. We've gone from paradigms down to modules. Now, how do we put those pieces together?
Well, it's interesting to look back at how we got here. Martin takes us on this history lesson. Early days, you had to specify the exact memory location for every piece of code. Can you imagine?
Talk about tedious. That sounds like a nightmare.
It was. As programs grew, it became impossible. Then came relocatable binaries, total game changer.
So you didn't have to micromanage memory addresses anymore. The computer could figure it out.
Exactly. Like going from individually placing each brick to prefabricating whole walls. Paved the way for true modularity.
And suddenly, building bigger, more complex systems became possible.
Precisely. Over time, as hardware got better, linking these modules became less of a bottleneck. We had the building blocks for components, but the question remained, how do we decide what goes where?
Right. How do we organize them well? What are the guidelines?
That's where cohesion and coupling come in. Cohesion is how closely related the things within a component are. Think of it this way. If a component's highly cohesive, everything inside is working towards the same goal. They belong together.
So the more cohesive, the better. Like a well-organized toolbox where everything has its place.
Exactly. Martin talks about 3 specific principles: reuse-release equivalence, common closure, and common reuse. Different lenses for thinking about grouping.
Now, our listener loves those aha moments, those insights they can apply right away. Which of these principles is most actionable?
Reuse-release equivalence is a great one. Basically, the things you group together, they should be releasable as a unit. Not just logical grouping, but how you handle changes over time.
Ah, so if you need to change something, ideally you change that component and nothing else. Minimize the impact.
Exactly. It's about making your system more manageable. Now, once you've got these nicely cohesive components, how do they relate to each other?
Right. We don't want them to be isolated islands. How do we make sure they communicate and work together well?
That's coupling, how components depend on each other. And one big pitfall is cyclic dependencies.
Cyclic. So component A depends on B, which depends on C, which depends back on A. Round and round we go.
Exactly. Leads to what Martin calls the morning after syndrome. You make changes, go home happy, come back. Everything's broken because someone else's changes clashed with yours. A tangled mess.
Been there. It's like that game where you pass a tangled rope around and everyone ends up stuck. No one can move without messing things up.
Perfect analogy. That's why avoiding cyclic dependencies is crucial. It allows for more independent development, smoother integration.
Makes sense. So cohesion within components, minimizing coupling between them. What else do we need to consider about those relationships? So cohesion within components, minimizing coupling between them. What else do we need to consider about those relationships?
Well, to really understand those relationships, we have to talk about stability. Not all components are created equal in that regard. Some are naturally more resistant to change.
Okay, interesting. So what makes one component more stable than another? Is it size? Complexity?
Think of it like this. A penny standing on its side. Pretty unstable, right? A little nudge and it's over. But a heavy table, that's stable. You need a lot of force to flip that thing.
Okay, I see where you're going with this. So in software, some components are inherently harder to change than others. They're the tables of our system.
Exactly. And the stable dependencies principle, or
Mm.
SDP, it tells us we should depend on things that are more stable than we are. If your component's likely to change often, don't rely on something even more volatile. It's like building a house on sand. You need a solid foundation.
Right. If my component is a bit wobbly, I need to find a sturdy table to lean on, not another penny. How does this connect to dependency inversion?
Remember those interfaces we talked about? They often represent stable abstractions. They define the what without dictating the how. That allows for flexibility in the implementation.
Because the interface itself is less likely to change drastically. Even if the implementation behind it does, it's like having a standard electrical outlet. You can plug in different appliances without rewiring the whole house.
That's a great analogy. And this leads to another principle, the stable abstractions principle. It states that a component should be as abstract as it is stable.
So the more stable something is, the more abstract it should be. That sounds a bit counterintuitive at first. Why is that?
Well, think about it. If something's stable, it's probably used in lots of places throughout your system, right? It's foundational. By making it abstract, you allow for future flexibility extension without having to rewrite everything that depends on it.
So
Yeah.
even the stable parts can evolve gracefully without causing a cascade of problems. It's like future-proofing our architecture.
Exactly. And Martin, he introduces this cool way to visualize all of this, a metric called distance from the main sequence, or D.
Wait, a metric, so you can actually measure how well your architecture is doing in terms of these principles. That's really cool.
You can. And it can be incredibly helpful, especially for larger teams where it's harder to keep track of everything, like an early warning system for architectural debt.
I love that analogy. Instead of things getting out of control and ending up in that quicksand scenario, we can use this metric to spot potential issues early on.
Exactly. It helps you see where you might need to refactor, rethink your dependencies to improve the overall stability, maintainability.
Okay, I'm starting to see how these principles all work together to create a more robust, adaptable architecture. But I have a feeling there's more to the story. Where does Martin take us next?
The next section delves into the art of drawing boundaries within a system. This is where things get really insightful, even philosophical.
Boundaries. So this is about separating different parts of our system, right? But where do we draw those lines? Feels a bit like trying to divide up an ocean.
Well, Martin emphasizes that boundaries should be drawn where there's an axis of change, places where things change at different rates or for different reasons. It's anticipating those points of potential friction and designing your system to handle them gracefully.
Okay, I see. So if two parts of my system are constantly evolving together, they probably belong on the same side of a boundary. But if one part is stable while the other's undergoing rapid changes, best to separate them.
You got it. Similar to the single responsibility principle, but at a higher level, minimizing the impact of change, making your system more manageable.
This makes sense in theory, but do you have any concrete examples of how this plays out in practice? How do we identify those axes of change?
Martin uses some really thought-provoking examples. He starts with this idea that the database is a detail.
Hold on. The database is a detail, but isn't the database like the heart of most applications where all the data lives?
That's a common misconception. He argues that the way we store data is less important than the data itself. Your business logic, the heart of your application, it shouldn't be shackled to a specific database technology. You want the freedom to swap things out as needed.
So it's not that the database isn't important, but we shouldn't let it dictate the whole structure of our system. We need to maintain that flexibility.
Precisely. And good architecture allows for that. You should be able to switch from a relational database to NoSQL, even to a simple file system without having to rewrite everything.
Okay, that makes sense. But how do you achieve that level of flexibility? Sounds like a tall order.
One approach is to embrace the concept of a plug-in architecture. It's a powerful idea, applicable beyond software too. Think of a system where you can easily add or remove components without disrupting the core functionality.
Like adding extensions to a web browser.
Yeah,
Or swapping out different modules in a game.
those are great examples. Martin uses fitness, a testing framework, to illustrate this. Initially, it didn't even have a database, stored data in simple flat files. Then, as the system grew, they considered more robust options.
So they didn't lock themselves into a particular database technology prematurely, kept their options open.
Exactly, and this highlights a key insight. Boundaries are drawn where there is an axis of change.
So if you know something is likely to change in the future in how it works or what it connects to, that's where you draw a boundary. You create that separation to minimize disruption.
Precisely. It's all about anticipating those points of friction and designing accordingly, kind of like earthquake-proofing a building. You need to identify the fault lines and build in flexibility to withstand the tremors.
I love that analogy. Okay, so I'm really starting to get this. Drawing those boundaries thoughtfully, anticipating change, minimizing its impact. But our listener loves to hear real-world stuff. Does Martin offer any case studies, examples from his own experience that show these principles in action?
He does. Appendix A is full of these fascinating stories from his career.
Excellent. What are some highlights, any stories that really stand out in terms of proving how important these principles are?
One that comes to mind is his experience with a system called DateNet 30. Early in his career, they were working with incredibly limited memory. We're talking kilobytes here, not gigabytes.
Oh.
And they had to figure out how to cram all their code into this tiny space.
Wow, I can't even imagine. That's like trying to fit an entire library into a shoebox.
It was a different era. But it highlights why modularity is so essential. By breaking the code into smaller, reusable pieces, they made it work within those constraints. A testament to the power of thoughtful design, even with limited resources.
So even back then, these principles were crucial. It's not just a modern concept.
Absolutely. Another story that really drives home the importance of abstraction, decoupling, his work on a project called SE, building custom modems. Initially, they didn't properly abstract the interface between their code and the hardware when they needed to swap out the hardware for a different model. Nightmare.
Oof, that sounds painful. It's like realizing you built your house around a specific refrigerator and now you can't replace it without tearing down the whole kitchen.
Exactly. By creating a clear interface, they could have avoided that mess. Swapped out modems with ease, just like plugging in a different appliance.
Okay, so these aren't just theoretical principles. They have real-world consequences. Failing to apply them can lead to some serious headaches down the line. You got one more story for us, something that really drives the point home.
One more cautionary tale. His experience on the VRS project. They chose a particular database, Unify, really early on. It ended up locking them in. When they realized they needed to switch, it was nearly impossible. Stuck with their initial decision, even though it wasn't the best fit anymore.
Ouch. Classic case of analysis paralysis. Making a big decision too early can really come back to bite you.
It can. Good architecture is about leaving options open, avoiding those traps, creating a system that can adapt to changing needs, technologies.
Okay, I'm feeling very enlightened by these stories. So helpful to see how these principles play out in real projects, both the successes and the cautionary tales. But what about the modern world? How do these principles apply to things like the web, all the frameworks we use today? It feels like the landscape of software development is constantly changing.
That's where things get even more interesting. Martin, he argues that, just like the database. The web is a detail.
Hold on, the web is a detail, but isn't the web like everything these days? So much software is web-based.
Easy to get caught up in the hype. But we've seen this pendulum swing before. First, it was all server-side, then client-side with things like applets, JavaScript. Now it's swinging back to the server with Node.js and all that. The tech changes, but the principles remain.
So it's not about chasing the latest trends, but about understanding those core design principles, no matter the specific tools or technologies, don't get swept away by the tide.
Exactly. The lesson for architects is don't let those trends dictate your core architecture. Focus on the essence of what your software does and treat the web as just another delivery mechanism. It's powerful, but it shouldn't define your whole system.
That makes a lot of sense. It's about keeping your eye on the prize, the core value, not getting distracted by the shiny new toys.
Precisely. Now, speaking of shiny new toys,
Yeah.
what about frameworks? It seems like everyone's using them these days. Lots of benefits, but
Right. Frameworks can be super powerful, save you a ton of time and effort, but they can also be a bit of a double-edged sword, can't they?
they can. And Martin, he has this insightful way of looking at them. He uses the analogy of an asymmetric marriage.
An asymmetric marriage. Okay, that sounds a bit ominous. What does he mean?
Think about it. When you choose a framework, you're making this huge commitment, structuring your code around it, inheriting its classes, following its conventions. You're tying your fate to that framework.
So you're going all in, but the framework isn't necessarily making the same commitment to you.
Exactly. The framework authors, they're free to change things, deprecate features, even abandon the whole thing. You're kind of at their mercy.
So, like, signing a contract where one side has all the power, that does sound a bit risky.
It can be. Martin points out that frameworks often violate the dependency rule, pushing their way into the core of your application. Once that happens, tough to extract yourself.
So what's the solution? Avoid frameworks completely. That doesn't seem very practical.
Not necessarily. They can be incredibly valuable. The key is to be mindful of that asymmetric relationship and to minimize your dependency.
So choose carefully and try to keep them at arm's length. Like a friendly neighbor, not a demanding roommate.
Exactly. Good architecture is about making choices that give you flexibility, minimize risk, creating a system that can adapt, even if that means switching frameworks down the line.
This is great advice. I love the analogy of the asymmetric marriage. Really highlights the importance of choosing those frameworks wisely, not getting too dependent.
It's all about striking that balance, leveraging their power, but staying in control of your own architecture. It's a delicate dance.
Okay, so be mindful of those framework relationships. Don't get too entangled. But where does that leave us in terms of actually structuring our system? Is there like a central component in clean architecture?
There is. It's called the main component. Think of it like the conductor of an orchestra. Doesn't play any instruments itself, but sets the tempo, brings everyone in at the right time, makes sure the whole performance comes together.
I like that. So the main component, it orchestrates everything else, but it doesn't actually contain the core business logic.
Exactly. And here's the interesting part. Martin says the main component should actually be the dirtiest part of your system.
Dirtiest. Okay, that's an interesting way to put it. Should I be worried about my code getting muddy?
Not literally. It means it handles all the low-level details, the messy stuff you don't want polluting the rest of your nice, clean architecture.
Yeah.
Reading configuration files, setting up database connections, handling command line arguments, that sort of thing.
So it's like a buffer zone. Shields the rest of our system from the messy realities of the outside world. Like an airlock on a spaceship, protecting it from the vacuum of space.
Perfect analogy. And this is where things like dependency injection frameworks can be super helpful. They make it easier to manage all those dependencies, keep them organized.
Dependency injection. That's one of those terms that makes people's eyes glaze over. Can we break it down a bit? What's the big idea?
Simpler than it sounds. It's basically decoupling the creation of objects from their usage. Instead of hard-coding dependencies within your classes, you inject them from the outside.
So instead of a component having to know exactly how to create the things it needs, those things are just given to it. Like room service, you call it down. I need a toothbrush, and it just appears.
Exactly. And that gives you a ton of flexibility. Swap out implementations easily, use mocks for testing, make your system more configurable without rewriting code.
Like a universal adapter for your software. Whatever dependency you need, plug it right in. But how does this tie back to our main component, our conductor?
Well, the main component's a great place to handle all that dependency injection setup. Once those dependencies are all nicely injected, the main component can then pass them along to the rest of the system.
Like a waiter serving up a perfectly prepared meal.
Exactly. It's a beautiful example of how a simple principle, keep the messy stuff at the edges, can have a huge impact on the elegance, the maintainability of your whole architecture.
I'm really starting to appreciate the beauty of clean architecture. It's all about making these smart choices up front to minimize complexity, maximize flexibility down the line. But I have a feeling Martin doesn't stop there. Are there any other areas where he applies these principles?
He does. There's a whole chapter on services, both great and small. And this is where it gets super relevant to modern software, right? Services are everywhere.
Services. So we're talking web services, APIs, microservices, all those buzzwords you hear all the time.
Exactly. And Martin, he starts by debunking a myth. The idea that just using services automatically gives you a good architecture.
Yeah, I can see how that's a trap. Just because you're using the trendy tech doesn't mean you've magically got a good architecture. It's about how you use those tools, right?
Exactly. The architecture is defined by the boundaries you draw, the dependencies you manage, regardless of whether you're using services or not. Services are a tool, a mechanism for communication.
Okay, so the question is, how do we use services in a way that actually contributes to good architecture? How do we avoid those traps?
One classic problem he points out is cross-cutting concerns. These are functionalities that affect multiple parts of your system: logging, security, transaction management, those sorts of things.
So if you're not careful, These cross-cutting concerns can get all tangled up in your services, creating messy dependencies, blurring those nice boundaries we've worked so hard to create.
Exactly. And it uses this funny example to illustrate it. The kitty problem. Imagine you have this system with several services, each responsible for something different. Then someone decides they want to add a feature that involves kitties.
Kitties. Okay, now I have to hear more about this. What do kitties have to do with software architecture?
It's silly, but it makes a point. If you're not careful, you end up having to modify every service to accommodate this new kitty feature. Add kitty-related code to your accounting service, your inventory management, your customer support. Nightmare.
Because the kitty logic has to be everywhere. Suddenly your clean, modular system is overrun with kittens.
Exactly. And it defeats the whole purpose of having services in the first place. You lose that independence, that flexibility.
So how do we avoid this kitty catastrophe? Keep our services clean and focused, but still handle these cross-cutting concerns.
Martin's argument is you apply those same solid principles we talked about earlier, but at a higher level. Cohesion, coupling, dependency inversion. Think about those, but for your services.
So carefully design each service internally to minimize those cross-cutting concerns, maintain that independence, like having designated play areas for the kitties so they don't wreak havoc on the whole house.
Exactly. It's all about clear boundaries, clear responsibilities, even within your services. That way you can add new features, like our kitty friends, without turning your whole architecture into a mess.
This is great. We've gone from bricks to buildings to whole cities, all while keeping those core architectural principles in mind. Feels like a really powerful way to manage complexity at scale. But I know our listeners want to apply this to their own work. What are the key takeaways? What can they start doing today?
If I had to boil it down. First, remember good architecture is a process, not an event. Constantly evaluate, adjust as your system evolves.
So not about finding the perfect architecture up front, but building something that can adapt to change. Embrace the evolution.
Precisely. Second, don't be afraid to challenge assumptions. Just because everyone's using a certain technology or framework doesn't mean it's right for you. Think critically.
Do your research, weigh the options. Don't be afraid to go your own way if it means a better system.
Exactly. And third, never lose sight of the core value your software provides. What's the essence of what you're trying to achieve? Don't get bogged down in the details, the trends. Focus on the heart of your application.
Keep your eye on the prize. Remember why you're building this thing.
And last but not least, good architecture. It's about choices that minimize the lifetime cost of your software. Make it easy to understand, maintain, extend for yourself and for whoever works on it down the line.
So it's not just about the code itself. It's creating that sustainable ecosystem for your software to thrive in, an investment.
Couldn't have said it better myself.
Well, I think we've covered a lot of ground in this deep dive. From the basics of software architecture all the way to services, frameworks. It's been quite a journey. I don't know about you, but I'm feeling inspired, ready to tackle some architectural challenges.
Me too. Always good to revisit these principles. Timeless for a reason.
Absolutely. So for our listener out there, ready to create some amazing software, what's one final thought-provoking thing we can leave them with? Something to ponder as they go on their own architectural adventures.
Think about those axes of change in your own projects. Where are those points where friction might pop up? Where could a bit more decoupling, abstraction, create more flexibility, resilience in the long run?
Excellent questions to keep in mind. Well, that's it for this deep dive into clean architecture. Thanks for joining us. We hope you found it valuable, and we can't wait to see what incredible software you create.